Hey everybody, and welcome back to Calc 3 Online. So the purpose of this video is to just kind of talk a little bit more about Green's theorem. I'm actually going to prove a little bit about how it works for a special case of regions, and do a few more examples, that kind of thing. Show you actually an application of Green's theorem where we can use it to actually find the area between two curves. So I'll show you that, which is kind of neat. So just a few different things kind of with Green's theorem. So this first one, this is just a problem involving work. So we can find the work done by the force, capital F here given by this, in moving a particle from the origin along the x-axis to 1, 0, then along the line segment from that point to 0, 1, and then back to the origin. So just like with any Green's theorem problem, I always recommend you start with plotting things out, kind of see what you're working with. So you're going from the origin along the x-axis to 1, 0, and I'm not going to mess it up this time. Put the x-axis on the right spot. And then, so we're going like that. And then we're going to go to the point 0, 1. Which I'm going to say is right about there. So I'm going that way, and then we're going back to the origin. So right there. So this little region right in here is my region D. And this is one where we're going counterclockwise, so it's positive orientation and all that. So the work here is going to be the line integral around the boundary of that, the yellow curve. Okay, we're going to try to color code some of this. And it's going to be that force vector, capital F, dotted with dr, right? So this is just, normal line integral, but this is where we can use, here, let's maybe do this. So we've got this is the same thing as p dx plus q dy, right? And so this is where I'll use my Green's theorem. So P is this, Q is this, right? And we know by Green's theorem now, this is the double integral over D, right? Again, let's maybe color code some stuff. And then it's going to be partial of Q with respect to X minus partial of P with respect to Y, dA. So if we go and plug all that in, partial of Q is going to just be, so this is my Q, with respect to X is Y squared. So we got a Y squared, and then partial of P, so again, P over here, with respect to X would be, with respect to Y would just be X. And then we got dA. And so now you just go and you look at your function here and you look at your bounds. So, the one that we're going to need is this part right here. That line, right, is just y equals 1 minus x. And so we can go and just kind of plug in everything nice now. So we're going from, if we do we'll just do a dy dx. So we're going to go 0 to 1 minus x, and then we're going to go 0 to 1, y squared minus x, dy dx. And everything here is really nice. If you're struggling with solving these things, please let me know, but we've done so many higher order integrals at this point. I'm just going to kind of write down what you should get, but in problem sets and things, I would still expect you to work out that stuff. But that's kind of the concept of the problem, which is the most important part here. So this is very much a physics problem. I took, I think, 2 college kind of level physics courses, and this is a very classic problem in those courses. If you go and be a physics major, Calc 3 will definitely be a required course that you would have had to take. And you just use vector calculus all the time. You're doing stuff like, just computing the work as you move around this triangle. And it turns out to be just a line integral, right? But then we can further simplify that line integral. And again, instead of doing, it would be 3 separate line integrals we'd have to add together. we can just do a Green's theorem, really quite a nice simple one, and then we got our answer. All right, so what I want to do now is prove Green's theorem for a type 1 region. And the proof in general, actually proving it for a type 2, let me first say, is really very similar. And I think you'll see when you see a proof of this that you could easily restructure it to be a proof for a type 2 region. And a lot of regions in the world are type 1 or type 2. But you could also just have, region D just being like some weird thing like that. And there's tons and tons of regions like this out there in the world. And to prove Green's theorem for these kind of regions is really, really difficult. And I actually didn't see how to do that until I took a course on differentiable manifolds. So if you want to Google that word up, see what that's all about, go for it. But I'm not going to talk about it here. So the proof in general is tough, but we can definitely sketch it out for regions like this, which are type 1, okay? And we absolutely could do it for type 2 also. We're just not going to because it takes a little while. So, so remember, Green's theorem says this. And so the idea is basically, since we can, the double integral can be applied to both of these, we could really, and also the single integral could be applied to both these, right? We could really rewrite Green's theorem this way. All right, so all I did is I basically split this, right? And then I split this too, and I did flip the directions here. So there's going to be a reason for me to do that. So what I'm basically going to do is if I can show that this equals this, right? And if I can show that this part equals this part, right? Then that would actually prove Green's theorem, right? If you just show those two things are equal, then adding them should definitely be equal, right? Adding these two should be equal to adding these two. So that is the idea of the proof. That's how we're going to do it, right? And I'm going to start, and I'm going to work with. I'm going to start with work with these things in yellow. So I'm going to show this is equal to this. So right here, I'm going to basically set up that double integral over D. Okay, so we've got like partial of P with respect to Y is like a function of X and Y. Let's just do dy dx, right, because it's a type 1 region. So being a type 1 region, we have like G1 and G2 functions of X as like the bounds, for Y. So we got like G1 of X down here, lower function, G2 of X up here, upper function. And then we've got, A and B. A and B for the X bounds, okay? So if I do that first integral, I would just get this, right? Literally it's just fundamental theorem of calculus, but it's like with the Y, right? Because I did the integral with respect to Y. So I just basically put in G2 in there. And the integral takes care of the derivative for me, right? If I do a dy integral, I have a dy derivative, so that's why that part's also canceling out, okay? So that is an expression for what this equals. If I can show that this equals the same thing as that, then equals the negative, right, of this, then I've got it. I'm basically done. So now I'm going to turn to the line integral around the curve for p dx. And I basically need to just do I need to do 4 different line integrals. Now 2 of them are actually going to turn out to be really nice. And actually maybe we can just say those ones right now if I'm already talking about it. So notice that the line integral for curve 2 of p dx is going to equal the line integral for curve 4 for p dx. And notice that they would both be equal to 0. And that's just because we're doing a dx there, and there is no change in x because it's a vertical line, right? So these two would go to 0. So actually, all of a sudden 4 of these line integrals reduce really to 2. I only need to worry about this one and this one, okay? So for curve 1, I'm going to let just like x equals x, and then y will equal like g1 of x. Okay, this is just like me parameterizing my function along curve 1. And so in that case, the line integral around curve 1 of p dx is going to be going from a to b, right? And then I'm going to have p of x comma g1 of x, and I still get a dx, right? All right, that one's not too bad. And then, so let's actually kind of block some of these off. So then for curve 2, I'm going to do the same thing, let x equals x, and then y equals now g2 of x, right? Then line integral of curve, it's curve 3. Around curve 3 of p dx, right, is going to equal, so I'm actually going to do a little bit different change here. I'm going to do negative of minus c3 because I want my bounds to be the same. So I'm just flipping the order because I want the a and b to be in the same direction. So then I have p of x, g2 of x, dx, and if I take it, so instead of going normal curve 3 direction, I'm negating and I'm going negative curve 3, right? Which is still the double negative is gonna work out and it's gonna give me the correct orientation. But the nice thing is that if I do this, then I go, so I have minus a to b, which is the part that's nice because I'm gonna combine these integrals in a second. And then p of x, g2 of x, dx. And so that is my other kind of line integral. So now, putting it all together, I have the line integral around, so actually I'm going to erase this just so I can write this all down somewhere. So I have the line integral around the curve for p dx is these 4 line integrals of p dx. But, down here, we talked about how curve 4 and 2 go to 0, right? And then I need to basically pop this in and pop this in, right? And so if you do that, then this would actually equal that thing, right? And if you look at this, right, so I wanted to show that I can get this, right? So I had a to b on both of them, right, which I have a to b on both of these. So that part's good. And then I have the G2 one is the positive one, and here the G1 is negative. Here, the G1 is positive, and the G2 is negative, right? But if you remember, I wanted to show that p dx equals the negative of that double integral. And so that does it, right? This thing is the negative of this orange line. And so that shows that this would equal this, okay? And that is actually kind of how the proof goes. So what you then have to do is just do q dy equal this. And I'm not going to go through it because it's literally the same idea. It's a good thing to try and work through yourself. But the process of proving this and this is literally identical here. And so then you add together these two, and then it would have to equal these two things added together, and that would prove Green's theorem for a type 1. Definitely doesn't prove it for anything else, but a lot of things are type 1, so it's actually pretty good. So that is actually how it works. It's really a true thing in math, and it is very, very handy. I wanted to show you this problem too. So a lot of times students get used to, and this is fair, because to do a line integral around like a triangle or something, we've seen a lot of triangles, but you would have to do 3 different line integrals, right? But you can speed that up if you just do the double integral once over the whole region that it encloses, right? But there's actually an interesting way to use Green's theorem kind of in a reverse direction, and that's with like finding areas of regions enclosed by like parametric equations like this. And they don't even have to actually be parametric. I mean, I could ask you to find the area of like region enclosed by like an ellipse or something. I think there's a problem in the book about that. And then the way you would do it is actually, you would still have to parameterize eventually because you would be solving a line integral. That's how we do this. But this is kind of the idea. So we know that the double integral over some region of 1 like dA, right, is literally the area of D, right? We've seen that before in chapter like 15. And so in the context of Green's theorem, right, if you're doing a double integral of partial of q with respect to x minus partial of p with respect to y dA, you could utilize this, right, if, I'm going to do that a little bit better. If partial of q dx equaled, minus partial of p with respect to y, that subtraction equaled 1, right? So I'm just saying, like, set this up so it is a 1, just like this is, right? And there would be lots of ways to do that. I think that there's probably infinite, but there's a few that are really nice. Okay, so if p equaled 0 and then q equaled x, notice here that you would get, like for this result, you're going to do the partial of q with respect to x, which is 1, and then minus partial of p with respect to y, which is 0, and that equals 1, right? You could do p is equal to negative y and q is equal to 0, and this would also do it, because now you're going to do 0, right, minus a negative 1, which is 1, and that's good. There's one, though, that seems to be used the most often for this, and it's p equals to negative a half y, q equals to 1/2 x, okay? And in this one, right, same thing, partial of q is going to be, with respect to x, is going to be 1/2, right? And then minus partial of p with respect to y is negative a half, and so then you'd add those and you'd get 1. So all of these can kind of be used here. You can basically do the area as a line integral around C of either x, let's color code this a little bit. So you could do line integral on C of x dy. That would come from this one, right? So p is 0, q is x. So in my Green's theorem, right, you would be just getting x dy, because it's just p dx minus or plus q dy, right? And so these two in here would simplify that way. So maybe just in general, I'll write it again. P dx plus q dy equals the double integral over d. That's just Green's, okay? So, that's 0. So then this line integral reduces to x dy. Or you could have the one in purple, which is, let's see, so it's going to be negative the line integral around C, and then you'll have y dx. That would also give you area, right? So again, just using this and popping these things in here. Popping these things, I guess, in here to give you this. And then last but not least, you could have 1/2 the line integral x dy minus y dx, okay? And so these are actual theorems, they're in the text too, but they would literally give you area of like a region. So I have a region that's parameterized here, and so another way to find area in math is to actually do a line integral and they are closed loops, right? Because they're area of like enclosed regions, right? And so I can do any of these. A lot of times you'll see this one done the most, and I don't really know why actually, but they like that one. I just want to kind of go through and show you how I can do it for this. So I'm going to actually erase some of this so I have room, but I'll put down the most important stuff here. All right, so that is my area kind of formula that I'm going to use. So find an area with line integrals. Areas of two-dimensional objects with line integrals. Oh, math. So I am going to start by just plugging in what I know. So I got x is t cubed minus 6t. I've got dy is just going to be 14t. And then minus y, which is 7t squared. And then dx is let's see, that is a 3, right? 3t squared minus 6, and then dt. Okay. So then the one thing you just have to figure out is the intersection of this, like what region, two-dimensional region are we finding the area of, right? So you also have to know, like, you have to set t cubed minus 6t equal to 7t squared and solve, okay? So basically you're going to get this cubic, which does factor somewhat. And so you can see right now, like, one of them is t equals 0. So, and then there's going to be these other intersection points right here. All right. So this is one of those annoying quadratics because it looks like it should be so nice, but you're definitely getting a root of 0 there. I'm actually sick of the orange color here. Let's do something else. Here, this looks like it should factor, but it doesn't. The roots there are just 7 plus or minus square root of 73 over 2. So you can just do like quadratic formula and get those. And so, you know, what it becomes now is that there's these like multiple intersection points, and, you know, in the context of a problem, it might be that t is time, and so you don't want like negative time. And so, you know, one of these, so 7 minus the square root of 73 over 2 is going to be negative because square root of 73 is bigger than 49. Like 73 is bigger than 49. So this is negative. And so 7 plus the square root of 73 over 2 is positive. So those become my bounds. Like maybe I would only be concerned with 0 to 7 plus square root 73 all over 2. And so now it's really just a single variable integral. You solve that out, and you've actually found the area of the region in the positive t's that is formed by these two parametric equations. So that is how you do it. I'll put the answer down here too, but at this point it's honestly just a lot of plug and chug. So I just went to a calculator and plugged everything in. Definitely not a nice answer, really, because of this bound down here is really messy. So it's about 2.4, we're just going to say 7 units squared, whatever units those are. So yeah, but the concept is what I really want you to see. So this is actually a formula that we use to find area of some enclosed region given by, like, it doesn't even have to be given in parametric, but you would parameterize it to get it to work with this eventually. So, it might be just like asking you, like I think there is this one in the book that's like asking you to do the area of an ellipse, and you would have to parameterize the ellipse first, and then go from there. So it's kind of neat. One last thing I want to do. So in our conservative vector field section, there was, we talked about these different ways that we can check to see if something is conservative. And we had this theorem that said, given some PQ field that is open, simply connected, that's on an openly simply connected region D, so like a nice one, right? If it's that nice region and the partial of P with respect to Y is equal to the partial of Q with respect to X throughout all of that region, then F was conservative. That's like a very handy tool for us to check for these conservative vector fields. With Green's theorem, we can actually prove that result now. So this is all pretty quick. So if we've got like the line integral f dot dr, right, that is this line integral p dx plus q dy. And so here's the Green's theorem part. So by Green's, right, we know that that should be the same thing as partial of q with respect to x minus partial of p with respect to y dA, right? But if we're proving this, so we have this part is one of our like assumptions here. We have that to work with. We want to prove that f is conservative, right? So if these two things are equal, that's right in here, right? If, this is 4 and this is 4, you're doing 4 minus 4, so you're getting 0, right? So that whole thing goes to 0, not to 6, but to 0. So then this double integral is really of 0 dA, which is 0, right? And so what that proves, right, is that the line integral around this closed loop of like f dot dr here, this is equal to 0. And we also had a result before in that last section that said if that line integral around a closed path is, if this thing equals 0, then the line integral is independent of path in D, right? It's actually an if and only if, so that's just what it means, right? It doesn't matter, which way you go around your loop. Any way you want to go, it's just equal to 0. This is true for like an arbitrary path, right? So it's independent of path, right? And then we have another result that says if a line integral like this is independent of path, right, in D, then f is conservative. And that does it. Okay, that proves it. So super kind of nice connection between Green's theorem and our past section on conservative vector fields. So it's just something I kind of wanted to pop in here at the end. But most of the time, what you're going to use Green's for is you're going to use them for like what this first example is. You're basically, instead of doing 3 or 4 or 5 or 6 or whatever line integrals, right, you can just do one double integral over the big region. It's a super shortcut, and you can imagine as you get more boundary curves, right, it saves even more time. And a lot of things that are really, really weird shapes have like tons of boundary curves to them. So we can do all of our work really quick if we just do a double integral.